Hello students, welcome. We'll continue with our lecture on reservoir and dam planning, and today we are going to discuss one of the most important topics, subtopics of this chapter, that is the reservoir capacity and reservoir sedimentation. So to begin with, let's understand what capacity means. Okay, so now you have constructed a dam. Now you are after the construction of a dam, there will be a reservoir formation upstream of the dam. But what should be the capacity? How would you decide upon capacity? For instance, there is a Chuka Dam. Now, people who constructed that dam, how did they decide how much quantity of water the dam has to store at any particular point of time? So that is what we're going to study. Okay, to get straight onto the topic, let's first understand two things, that is cumulative flow and demand line, that is also cumulative. So let's understand what cumulative means. Okay, now what happens is, if there's a river, okay, for instance, let me draw a river here, and at this point you are measuring discharge. Measuring discharge means you are measuring how much water is flowing through this river, and when you plot this discharge versus time, you will get something like this. This is a curve. That is what is known as hydrograph. This is known as hydrograph. Okay, pH hydrograph. Now from this hydrograph we construct what we call by the cumulative mass curve. Cumulative mass curve means you simply add on the values of previous value. So what I mean is, let's say the discharge for today is discharge and I should have written time and discharge. Okay, so let's say you have time and you have discharge. Let's say today, okay, today day 1 is 10, tomorrow or next day is 2 is, let's say, 11. Okay, so cumulative, how do you calculate cumulative is today is 10. Okay, now for next day is going to be 10 plus 11. For third day is going to be, this is 21, right? So 21 plus, let's say this is again 10. So here the cumulative is going to be 21 plus the new value, that is 10, that is going to be 31. So this is the discharge which I have drawn here, and this is the cumulative, or we call it mass curve. Mass curve is simply you add the previous value to existing and you continue the process. Okay, so what happens is, eventually what you're going to get is, you're going to get a curve, that is what you call by a mass curve, and the mass curve will always increase, like it is shown here in this blue color. Okay, so that is the mass curve. Yes, now this mass curve, as I explained, this mass curve is drawn with the actual inflow data. Now this dotted red line is what you call by the demand line. Demand line means, you understand what demand means, right? Demand means how much water you need to supply, how much is required. That is what we call by demand. So if you also plot the cumulative demand, so it's going to be, if it is a constant demand, so every day if the demand is, let's say, 10 or 20, then the line, okay, if the mass curve of this demand is going to be a straight line, which is shown here. Okay, so when you overlap this two, you are going to get something like this, that is shown here. See, the demand line you can see here, right? The demand line with this blue, yes, and the sorry, not the demand line, the mass curve, inflow mass curve is given by the blue line, yes, and the demand line is given by the red line. Now when you overlap over the same period, okay, it has to be in the same period. The time of the both the demand and the mass curve should be consistent, which means it is a common axis. Okay, time is a common axis. All right, so when you plot it, you will realize that some point of time this mass curve is meeting exactly the demand line. Sometime the mass curve is below the demand line, sometime it is above the demand line. Now what information does it give is, at a particular time, now let's start from this point. Let's start from this point A, where I'm assuming that reservoir is full. When this two line and this is coinciding, I'm saying, okay, just for purpose of explaining things, I'm saying at this point the reservoir is full. And eventually what happens is, you will have to the from the reservoir water is drawn out, right? Water also flows. What happens is, and again it also depends upon the inflow. So at this point, from this point onwards, let's say this is T1, from this time onwards the inflow was very less. Inflow to the dam was very less. So what happens is, when the inflow is less, this line becomes kind of a horizontal, okay, and again the inflow was very less, and then it gradually increased, which means inflow was steadily increasing. It is increasing at a snail's pace, okay. So at this juncture what is happening is, demand is more than the actual inflow. So here the volume of water is deficit. Now we cannot provide, the reservoir cannot provide this amount of volume to whatever is the required project or the hydropower project. So we are deficit. So the line that is vertical intercept, okay, let me use the term vertical intercept. Vertical intercept between this demand line and this inflow line is what we call by the deficit, okay. This intercept, this is the volume of water that is at this particular time T3, let's say, okay, at this particular time the reservoir is in deficit of this, okay. And moving on, again let's say this is in winter. In summer again the flow will start to rise, right? The inflow is started to rise, and what happens is it finally meets this point, which means again as I have explained in the this case, at this point the reservoir is full. When it is full, because it is in summertime, this inflow is increasing, right? Inflow is increasing here. When inflow increases, it is going above the demand line, which means this is surplus water. This much vertical intercept is the surplus water, which means we can meet the demand as well as there is surplus, which means it's additional water. We don't need this. Has to be reduced. This has to be now flushed, or we have to simply let it go. Okay, so when we decide about the capacity of a reservoir, these two, this deficit and the surplus may not affect, but this deficit matters, because this much of water we have to store. To meet the demand, this much of water has to be stored, which means this much of water has to be available always in the reservoir. Then only we can meet the demand, right? So these factor makes the deciding factor to how much capacity a reservoir has to, we have to build a capacity. I mean, what is the capacity of the reservoir? To decide upon this vertical intercept plays a very important role. Okay, so I hope that was clear enough. Okay, so now let's understand the same principle with help of an example. Okay, so here the question says the runoff from a catchment during a successive month in a year is given below. So January, February, so that is the runoff in million meter cube. Okay, million meter cube means this is a volume. Determine the maximum capacity of the reservoir required if the entire volume of water is to be drawn off an uniform rate without any loss of water over the spillway, right? So what they are saying is, this much of inflow is there. Now you have to design, you have to give the capacity of the reservoir so that we can draw and draw water from the reservoir at the uniform rate. So how do you decide this? Like I said, we have to start with plotting the mass curve. Now, so how do you construct the mass curve? We do the cumulative, values of the runoff versus time, right? So how do you do that? So for the first value 1.3, 1.3. For the next value, you add this 1.3 with this one and you will get 3.3. So 1.3 plus 2 is 3.3. Next, this value you take and add it with the next value and you will get for that value the cumulative. So 3.3 plus 2.7 is 6. Again, you take this value, add with this one, you will get this one. Similarly, you add this one, you will get this one. Now next step is you simply plot. Okay, you simply plot. Now you see this blue line is the mass flow. Okay, this is the mass flow curve, and we were able to plot it by doing the accumulative value, and we call it cumulative, right? So from here, how do we decide upon the reservoir capacity is during the month of March, the reservoir is at its lowest level. Yes, it is the lowest. Yes, this much water is there. In the month of August, somewhere here, this much water is there. The inflow is, the cumulative inflow is this much. And let me use a different color so that it does not mix up with the color that I've already used. Okay, so let me use a different color. I think this one is good enough. Okay, so here, this is the maximum point, this is the minimum point. Yes, so what we do is we simply draw a tangent from this minimum point and we draw a tangent from the maximum point, and this vertical intercept is what is the volume of water that we have to store. So this value gives us the actual capacity of the reservoir. Okay, so that's how we do it, and it is inconsistent with what I have explained previously. Yes, you take the minimum value, you take the maximum value, you draw the tangent, and then the vertical intercept is the volume of water that has to be stored to meet the average outflow or average demand. Okay, so that's how we decide upon the capacity. Okay, let's move ahead, and now we're going to start with the new topic, that is sedimentation in a reservoir. As I've explained in previous classes, that sedimentation means the amount of the sediments, right? The soil particles, the small rocks particle that river carries along with it. So when it carries along with it and you are building a dam across a river, what happens is velocity of that river is certainly, it is zero at the dam side. So all this load that the river was carrying previously, because the energy of water had the energy, now water does not have this velocity because of the construction of dam. So it will simply start to deposit. So if you, this is the profile, okay, this diagram shows the profile of a dam. So from the, if you start from the, so start from the point where the ponding has started, what you will see is eventually water is very turbid, right? And then those material that the river was carrying, it will start to deposit because it has no energy to carry it further down. So it will form a deltaic region in the way upstream of a dam. Okay, above that dam, above this delta formation, what happens is there is a sediment laden water, which means the concentration of sediment is very high, and we call this as a density current. Density current is a layer of water that flows at the bottom of the reservoir, whereby this density, this layer has a density higher than that of the rest of the water in the dam, in the reservoir, because it is carrying so much of sedimentation. And usually it is said that it does not mix well with the water because the density has the, it has some mass, right? The particles has some density, it has some mass, and it always comes to the bottom because of the velocity, a little bit of velocity of the water, it flows along with it. Okay, that is what we call density. Now here comes the main important part of this river sluice. If we construct our river sluice at exactly at this location, then this portion of sediment will be flushed out. So the amount of sediment that is going to settle eventually in the reservoir will it will be, these sediments are efficiently flushed out. So that's why we construct the river sluice at the region where there is a density current. Okay, and this is the typical diagram showing you the various formations underneath a reservoir. Okay, so first the deltaic formation, and the small sediment starts to sediment. Small sediment that is carried by the water will start to sediment over the, there will be a sedimentation process, and it will start to settle down in the bottom. Eventually this will lead to, this will fill up the dam. Okay, that is not desired, but it will take a long time. To reduce that sedimentation, this river sluice is constructed to flush out this sediment laden water. Now, as I have explained what sedimentation means, I have also explained the various I have explained how sedimentation actually occurs. Now let's understand the uh, what uh, leads to the sedimentation factors that can lead to a sedimentation. Okay, first thing is the nature of soil in a catchment. I have explained what catchment means, right? If the soil is kind of a loose, easily erodible, then the river is ought to carry more sediment, and eventually this will get into the reservoir. As such, we may not have any remedial measures for this because it depends upon the geologic formation of that region. So if it is there, so it would be there, so we cannot do anything about the nature of soil in the sediment. Of course, we can do plantation, whereby the erosion and loose soil, the amount of erosion and amount of loose soil that is being carried out can be controlled. So that is by doing afforestation if there is a deforestation, or we can do such kind of small scale measurements. But of course, it largely depends upon the soil, and there's nothing the humans can do about it. Next is the vegetation cover. If it has no vegetation cover, then it is easily erodible, so then all the sediments will get into the reservoir. Topography of the catchment. Topography, if it is like Himalayan catchment, very steep slope, then it says that more sediment will be the energy. The river has more energy to carry more sedimentation, right? Sediments along with it. Intensity of rainfall. Higher the intensity, it has higher capacity to flush out the topsoil. Eventually it will lead to the this material will be taken to the river, and river will take it to reservoir. Now next thing is, how do we measure this sediment load? So there are two types of sediment. One is the suspension, right? Suspended load. Suspended load means, which is you can see in this image, which is there in the in the which is suspending, okay, because of the buoyancy force, okay, which is not settled down. And there is a bed load. Bed load is the all the boulders and relatively larger particle. It will not float, but it will move along the riverbed, because there is the continuous force of river current, right? So river current is carrying the sediments from river sediment. These sediments are being carried by the river current along the river bed. Okay, and how do we measure is, it is said that we take a sample. Okay, we take a sample. Where is it? So we take a sample of river at a various depth, and we filter out the water, and when you filter out, some sediments will remain in the filter, right? So that filtered sediment is measured and weighed, and it is expressed in parts per million. Okay, and usually the bed load is taken as 15 percentage of the suspended load. So if, let's say, if it is 100 ppm, if the suspended load is 100 ppm, then the bed load is considered to be 15 by 100 into 100. Okay, so this much value is considered for the bed load. Okay, now next one is the trap efficiency. Now trap efficiency is a parameter that gives us how much sedimentation will happen in a reservoir. You are constructing a reservoir, sedimentation will happen, right? So how much in percentage, how much sedimentation may happen in the reservoir. So it is expressed as sediment retained into the reservoir by the total sediment that water river was carrying. Okay, and you multiply by 100 to express this in percentage. And it is found that, and it was first studied by Brunei. Okay, it was found that as the capacity inflow ratio increases, the sedimentation, the trap efficiency also increases. Trap efficiency gives a it isn't expressed in percentage, as I said, but it gives us information about how much sedimentation will occur. More the trap efficiency, more the sedimentation. That is the understanding. Okay, so capacity inflow ratio, if you plot this capacity inflow ratio with the sedimentation of particular reservoir, you will always find that as the reservoir capacity increases, the sedimentation also increases. So this was first given, this study was first conducted by the Bruni, and he has found out that the trap efficiency is a function of capacity inflow ratio. Okay, so If capacity inflow ratio increases, sedimentation increases. So for in a general understanding, large dam, large reservoir, more sedimentation, small reservoir, less sedimentation. If we have to directly translate this understanding to layman, then that's how we translate it. Bigger the reservoir, more the sedimentation. Smaller the reservoir, lesser the sedimentation. Logical, right? But this is how he was able to mathematically express it. And and the next term that we have is useful life of a reservoir. So as the name itself suggests, what happens is in due time, there will be, the capacity of reservoir will decrease till it reaches a stage where the reservoir will not be able to serve the intended purpose, and we call it the useful life of that reservoir is over then. And this basically happens because of the sedimentation. Okay, so once the intended purpose, it is not able to serve the intended purpose, then only way left is you do the complete removal of the sediments, which is going to be expensive, or you simply discard that reservoir. But it is going to take very long time, okay, to happen. Now, measures to reduce sedimentation. So what are the measures that would case, to what is there is the measures that can reduce this sedimentation? Let's discuss on this. The selection of a suitable site, and this comes time and again, even for construction of a reservoir, construction of a dam. We have to, primary thing is we have to give the proper investigation. We have to have a proper investigation while doing this selection of a site. Okay, if the inflow is carrying more sediment, it is odd that there will be more sedimentation. Okay, where if the catchment area is kind of a loose, and then it can be eroded easily, then of course there will be more sedimentation. And it is also said that should not be built on a downstream of a confluence of a tributary carrying large amount of sediments. Okay, next is proper design. So the rate of sedimentation is low in a reservoir of a small capacity, right? We just discussed this. So reservoir may be designed in such a way that capacity is increased in stages. So this is interesting one. In fact, you first construct a small dam. Okay, now the reservoir is only this much. Now the ponding is only this much. Once it gets filled and this is no longer able to serve its purpose, now why you are keeping this small at the initial stage is because you want to have the capacity inflow ratio low, because we know that capacity inflow ratio increases, sedimentation increases. Now how you can give a logical interpretation on this is, when capacity is low, and what happens is, there will be some velocity, because of which the sediment will be in a suspension mode, and this simply gets flushed out. It will not have sufficient time for it to settle down for small reservoirs. That's why the sedimentation is low for a small. And next, what they do is, once this useful life of this small dam is over, then they construct another dam over this. So this is in the second part. This is part 1, this is part 2. Okay, next stage. Now again, this will be your normal bed. So again, the capacity is low, therefore the sedimentation is going to be low. Again, in the third stage, you would construct like this. So that's how they do it in stages to reduce the sedimentation. And the time usually would be, time taken in this process to fill up the dam or the reservoir is going to be way more than if you have constructed at one goal. If you have constructed a dam at the one stretch, a big reservoir, simply because the capacity inflow ratio is going to be high for the larger reservoir, and quickly this reservoir is going to get filled. Okay, and yes, now I explained this, right? And the provision of a sluice gate, reverse sluice gate, right? So the density current or the water laden with sedimentation, if there's a provision to flush out this, then the amount of sedimentation is of course is going to get reduced. Okay, now measure to